This is Neil Patwari. I'm going to talk about a diagram that I've put together that shows how different quantities in the wireless system link budget are related to each other and how we use them to solve problems. This left-hand side where we see parameters that are dealing with the probability of bit error and the bandwidth. Most recently, we've been talking about the relationship between modulation and the probability of bit error and the probability of symbol error. But these are functions of the EB over N naught ratio. If we're given a probability of error requirement and we're told what modulation to use, that is going to specify what EB over N naught we must have at a minimum in order to achieve that requirement. We can convert that into the C over N naught ratio using the bit rate. Again, we may have a specified bit rate that we have to achieve. So computing the C over N naught ratio would require solving this equation for C over N naught as a function of EB over N naught and RB. And using that C over N naught ratio then to compute the received power. Again, if our receiver has a given equivalent noise temperature, then we can calculate the N0 and then use it to compute C. If we're also given other specs of our transmitter, transmit power, our antennas that we're using in the system, other losses, and the frequency at use, we can calculate the path loss, and then we can calculate the maximum range of our system. So we can see how that given these things I've underlined over here, we can go through this plot to find the path length that is possible with our communications link. Okay, the other direction is the way that we can go too. We can have our transmitter and receiver parameters given, like the equivalent noise temperature, the path length. We can be given these in addition to the transmit power, the antenna gains, the frequency and wavelength, and any other losses in our system. And we can work our way through the path loss model to get the received power. We can then compute the C over N naught ratio. If we know the bit rate that we're shooting for, we can compute the EB over N naught ratio. And using the modulation that we have either decided on or that we're going to try, we can compute the probability of bit error. If that probability of bit error is too high, we can try a different modulation. We can choose one with a lower M. We can choose a more robust modulation that has a lower probability of error for the same EB over N naught ratio. And we can do this until we meet our spec for the probability of bit error. So we can also go from right to left on this plot. These functions are something that we've been talking about, these probability of bit error formulas. This relationship here is something I talk about in the video lecture on EB over N naught. These formulas for received power for the freeze model and for the path loss exponent model are something I talk about in that video lecture. And then finally, the bit rate, symbol rate, and bandwidth is something that we've talked quite a bit about when we talked about pulse shapes. So all of these relationships are kind of tied into this one plot to try to map our flow from one side to the other to allow us to get to the goals that we want to get to. So I refer to this plot a lot, and you'll see it in some of my future videos.